It's memes like this that just really make me laugh. So don't forget, no matter what we are looking at in terms of our carbonyl chemistry here, lithium aluminum hydride is very powerful with the force. It is a very strong reducing agent. So it will reduce carboxylic acids, aldehydes, ketones, esters, amides, nitriles. We have not gone into nitros or azides, or we saw epoxides last semester, but this just meme just is classic. So on that note of hydride reagents being uber reactive, let's just talk about all the things that lithium aluminum hydride can do. In this chapter, specifically chapter 20, we're identifying that lithium aluminum hydride can react with all of the carboxylic acids and their derivatives. And what we get is either an alcohol or an amine from that reaction. Now, carboxylic acids with lithium aluminum hydride produce primary alcohols. Acyl chlorides also produce primary alcohols. Our anhydrides reduce all the way as well. And you guessed it, esters, primary alcohols. Now, once we get to the amine and the nitrile, now we see that nitrogen is incorporated, not oxygen, right? So nitrogen is a worse leaving group. Oxygen is a better leaving group. And so when we see an amide react with lithium aluminum hydride, we end up with a primary amine. Same thing with the nitrile. That nitrogen sticks on there like glue. So be very, very aware of counting carbons here. In all of my reactants, I had 2 carbons, even down to our nitriles and our amides. And so all of those products need to be also correlating with those number of carbons. Trickiest one there, in my opinion, is the nitrile. Don't drop that carbon. Now, if you're stuck in a synthesis and you want to go back to our aldehydes, you want to use a less reactive hydride reagent. Now, these were our 2 options. The lithium aluminum variety here with our tri-oxygen component, or tri-ether, is solely for acyl chlorides, all right? And so when those acyl chlorides react, you can stop at the aldehyde. Dibol H is the reagent to use for esters. Those again are both hydride reagents, but you can tell just by the acronym or by all of the things going on in these reagents, they are poisoned reagents. They are less reactive, and so they get to stop at aldehydes. Lithium aluminum hydride cannot stop at the aldehyde. Now talking about our Grignard reagents, our carbon nucleophiles has a very similar outcome as our hydride nucleophiles. Grignards are highly reactive. They contain a carbon with a nucleophilic center, something like a negative charge to pair with that metal, magnesium. And so that nucleophile, again, adds twice, right? When we have our acyl chlorides, our esters, or our anhydrides, Grignard reactions react very fast, and they will react twice to add on 2 identical R groups onto that carbonyl. Same with our esters, and same with our anhydrides. Notice here we have tertiary alcohols because the Grignard is so reactive, 2 equivalents of our Grignard will be added. Don't try to use 1 EQ of that Grignard. You will get a mixture of products and it will be a mess. So you do have to assume excess here And note that 2 R groups of the Grignard will get added onto your carbonyl compound to reduce it all the way down to the alcohol. Cuprates are less reactive. Cuprates are the copper version or the Gilman reagents of our organometallic compounds here. Now, just like before, the Gilman reagent is having a carbon nucleophile. We can kind of think about that carbon nucleophile being paired again with a metal. But notice here, those two simply mean that there are 2 equivalents of R group, but only one is going to react. The 2 are there to stabilize the copper lithium complex, but these again are less reactive in terms of our carbon nucleophilicity. So only one of our R groups will get added. And we know the drill. When one thing is added and we still have that leaving group, we can reform the carbonyl and we are left with a ketone. Now, ketones and aldehydes do not react with cuprates, which is why we didn't see them in chapter 19. So our Gilman reagents or our cuprates only react with acyl chlorides or anhydrides to make ketones. That's where you get to stop.